Hello everyone, thanks for coming. Today we are going to do a review of our week 4th lecture of linear algebra. So in this week, we talked more about the rank of a matrix, the vector space, and the dimension of a vector space basis. So how to determine the rank of a matrix? The rank of a matrix equals the number of non-zero pivots when we are doing the Gaussian elimination to reduce a matrix A to its echelon form. So suppose there are R pivot variables and n minus R free variables, then the number of pivots R is the rank of a matrix. The last n minus R rows of U and R are 0, and the solution exists only if the last n minus R entries of C or D are 0, and this gives n minus R independent conditions on the right hand side B. That's the solvability condition for the equals to be solvable. So how can we represent the solution to Ax equals to b when the solution is solvable? So the general solution could be written as x equals to xp plus xn, where xp is one particular solution. So particular solution is usually obtained by setting all free variables to 0 when we are doing the Gaussian elimination. And the pivot variables are the first R entries of D when we are getting the reduced row echelon form. Xn is the general null space solution. It is a linear combination of the n minus R special solutions. For each of those special solutions, we are setting each free variable to 1 in turn to get the special solutions. Pivot variables read from the columns of R when we are setting the free variables to 1. So the dimension of the solution space equals to the dimension. Actually, it's not a space. The dimensionality of the set of solutions is the dimensionality of the null space, while the rank of the matrix is the dimension of the column space. Next, we introduce vectors, linear dependence and independence. So given k vectors, they are linearly independent if the equation c1v1 plus c2v2 to ckvk equals to 0 only admits a trivial solution, which means all ci must be 0. If that is the case, then the vectors are linearly independent. Otherwise, they are linearly dependent. So how to test if a given set of vectors are linearly independent? We place them as columns of A, and then we solve A, C equals to 0. If there is no non-zero solution, then that means the given set of vectors is linearly independent. Otherwise, they are linearly dependent. So given a matrix, the R non-zero rows of an echelon matrix are independent, as the R pivot columns that are columns that contain the pivot variables are independent. Any set of n vectors in Rm is dependent if the number of vectors is greater than n, the number of entries. Given L vectors, we can then talk about the space spanned by those vectors. The space spanned by those vectors contain any vector that can be represented as a linear combination of those given L vectors. The column space of A is spanned by its columns, as the row space of A is spanned by its rows. We know that Ax equals to B, for Ax equals to B, it is solvable only when B lies in the column space. So independence of vectors concerns the uniqueness of combinations. Usually, if we have a set of linearly independent vectors, then the representation is unique. However, the spanning concerns coverage of the space. So that is to say, when we consider the spanning, some vectors may be redundant. Rank R measures the number of independent directions. So a set of independent vectors means no vector is a combination of others, while spanning indicates that every vector in the space is a combination of the given vector set. Basis actually means a set of vectors that can be called a basis of a space, means the set of vectors are linearly independent and they form a spanning of that space. In that case, every vector in that space has a unique representation in this basis. A basis is maximal independent set of a space and the minimum spanning set of a space. All bases of a space contain the same number of bases, and that number is called the dimensionality of the space, which is the number of vectors in any basis. Specifically, the dimensionality of Rn is n. Pivot columns form a basis for the column space of a matrix, and the rank equals to the dimensionality of the column space, also the number of non-zero rows in the echelon form of a matrix. Thanks for listening.